So today I'm giving two really very separate talks. One is called Unprojection. So there's a theorem and there's lots of applications. And the second talk is about deforming something we call closed tense to toric variety. So I gave some hints about what this deforming tense is about last time. So the reason for talking about these two things, which are really completely separate items, is because this will be this is a preparation for what we're going to talk about in 2 weeks' time. So on projection, there's a theorem called unprojection, and it takes a little bit of time to set up the material, but to say what it means. But just to, it's very easy to say what it states. So I have X and D. So these are local schemes. So X is spec of OX, and D is spec of OD. And I'm assuming two things. I'm assuming three things. One, X and D are Gorenstein. And two, the codimension of D in X is 1. Yes? So these are local rings. And I have these conditions on them. So maybe I'll say a few words about what Gorenstein is later, but the point about having a theorem is that it's a kind of place where you keep a piece of equipment, and you don't need to know what goes inside the piece of equipment to be able to use it. Right. So the result is then there exists a single element S, which is a homomorphism from I, D. So D is V of I in X. Or if you prefer, ID goes to OX, goes to OD. Right, so there's a homomorphism. ID goes into omega of X. So this is, of course, as you know, isomorphic to OX. That's the assumption, Gorenstein assumption, right? Such that the residue of S. So I'll explain a little bit what this is later. Residue to D of S in omega X is a basis. Right, so this means that omega X is omega D. This omega D is OD times this residue. Let me call it S bar. Right, so I'm assuming that X and D are Gorenstein. So omega X is isomorphic to OX and omega D is isomorphic to OD. Right, and I'm saying I can actually find a preferred or a preferred class of generators for the omega D. Okay, and I can define, if we define y to be spec of OX of S divided by relations SFI equals GI, then Y is again Gorenstein. Not local. Okay, so I'm stating a theorem as a statement in commutative algebra. And the reason for doing that is because that's the right place to state this theorem and to prove it. However, when we use it, I'll have to translate into geometry. Okay, so let me go through this again. So first of all, I need to say who this residue is and how I'm using these two conditions, right? And then I have to explain who Fi and Gi are. So this is Fi, and these are getting mapped to S of Fi equals Gi. Yes. So this is not very geometric. And later on I'll explain, when I come to the geometry, I'll say basically you can forget the theorem. The theorem is a very convenient technical tool, but it's not really that interesting to understand the proof. Anyway, so D in X is codimension 1 Gorenstein. So there is a dualizing sheaf omega x. So it's isomorphic to OX, of course. And what does it mean to have a dualizing sheaf? It means that the X functor, X again, I'm not quite sure against what, gives a perfect duality on the category of modules over X. Right? So I'm not especially interested in this. I'm just saying there is a categorical definition of dualizing sheaf, dualizing module. And then, so omega D, OD, and omega D is X1, OX, OD, omega X. So here's X, here is D inside X. And what I'm saying is I can consider sheaves on D as being a particular kind of sheaves on X. Right? If I know everything about how to do duality for sheaves on X, then I must know already how to do a duality for sheaves on D. Right? And sheaves, the kind of duality there is going to be some kind of X'd. And when I'm X'ing a sheaf on D into omega X, well, I have to go via OD. Right? So, there's a kind of Yoneda pairing and stuff like this. I mean, I'm not... all of this is very, very elementary material if you know the Grothendieck duality. Right? So I'm asking, how do you calculate this X1? Okay, so this is X1 from OD into omega X. And so if OD were, for example, a free OX module, we'd know exactly what it is. The X funct would then just be HOM and nothing else. Right? And so what we do is, so I'm going to write an exact sequence of sheaves. Here's OD, here's OX, here's the ideal of D. Right? So, if you think of D as being a divisor, then this is like the sheaf OX of minus D. Right? And so let's try, what I'm going to do is, I'm going to do the Hom star functor into omega x applied to this. Yes? So this starts with Hom OD into omega x. Right? I'm just treating all of this stuff as being sheaves on x. Right? So OD is a particular kind of sheaf on x. I can do Hom of OD into omega x. Right? And this is guaranteed to be 0. Right? It's 0 because D, all the sections of D considered on x are torsion sheaves. Every section of this sheaf does not have full support on x. Right? Whereas every section of omega x has so omega x does not have any torsion. Every section of omega x is supported on a component of x at least. Right? And so this goes to Hom OX omega x. Right? But that's just omega x. Right? This is true for any, I'm homming this Hom. Linear Homs from OX into any sheaf F is just the same sheaf F. Yeah? So that does nothing at all. And the next thing here that happens is this goes to Hom of ID into omega x. Right? So this looks like sections of omega x with poles on D. Right? If D was a divisor, if D were a Cartier divisor, for example, this would be exactly sheaves omega x with poles on ID. Right? And then this goes on to, this is the x1, the thing we want, OD omega x. Right? And then it goes on to 0. Right, goes on to 0 because OX is projective, so there's x1 of it into omega x is 0. Yes, and so this is the junction formula for D inside x. Right, it says that omega D is this thing Hom ID into omega x. Right, and so I'm really thinking of this as being like omega x with poles on D. Right, and then divide this out by omega x itself. So this is the guy that's not allowed to have any poles. So I think everybody knows the junction formula. KD is kx plus D restricted to D, and that's a particular case of this. Right? However, this works, you know, the x and the D can be arbitrarily singular, non-reduced, anything you like. D can be entirely contained, D can be non-reduced and entirely contained in the singular locus of x, or really whatever you like. I told you what I told you when this works. Okay, so the upshot here is that I have this exact sequence. 0 goes to omega x, which we know is just OX, goes to this Hom group, and that goes on to omega D, and we know this is just OD. Right? So if you think about this module, then I can take the element which is 1 in there and map him to, you know, something maybe I call him 1 in there as well. Right? And then there's another element, S here, that maps down to S bar, which is 1 in omega D. Yes? So this is just the definition of Gorenstein. This guy here is locally free, the free module of rank 1. Yes? And so there's an element here which is the basis. I can lift that basis element up to something in here, just because this is an exact sequence. Yeah? And so that's my element S here. So S is a particular homomorphism from ID into omega x, right? And, you know, the thing I'm saying here, the fact that it maps down to this basis element of omega d means, you know, this is a very precise statement, but very roughly it means that S has the maximum possible pole on D. Right? If we had if D was a divisor, it would mean that S has exactly pole on D. Right? So this is, so this says, this tells you who S is. Yeah? So the next thing I want is that, so I'm thinking of this as ID maps to omega x, and the omega x itself is isomorphic to OX. Right? So if this guy here is generated by F1 up to Fn, so look, incidentally, I started off by saying Gorenstein. If you know the commutative algebra, you won't worry about this at all. But if you don't know the commutative algebra, you should know that all rings, whenever anybody says Gorenstein, all rings are automatically assumed to be Noetherian. And Gorenstein includes, there's a well-defined dimension. Right? That's just part of the definition. So anyway, this ideal here is generated by finitely many elements, and each of these elements must go to somewhere, so just call them G1 up to Gn. Yes? And so the thing I'm defining is OY is OS, OX, with a polynomial ring with generator S, and then divided out by relations. And all the relations, this is all the relations there are like this. So these are linear relations in S. Yes? And so, so you know, here's a picture. Here's my X. Here is, so here's a little piece of X. It's local around there. And so here is A1 over X with coordinates S. Right, so if we were over a field and so on, then this would just be the product of X with A1 over the field with coordinate S. Right? What I've got is a section here. So this S is so the thing I'm writing is S equals 0. Right? S is a rational section. And what I'm writing is, so Y is the graph of S. Okay, so that's the statement. So you know, above the origin here, at the local point, I'm really thinking of the mainly interested in the case where this S vanishes entirely at the origin, and then the variety Y here. So Y is, this is OY is OX adjoined S, and then divided out by this S of Fi minus Y GI. Yes? So Y is just the graph of this rational function S. Right, and I won't say that S is that X is Gorenstein, that Y is Gorenstein. So Y is Gorenstein. So let me give a kind of pseudo proof. It's not entirely correct proof, but the point is that I have ID in OX, and I have the image of S, I, N in OX. Right? And so, you know, the thing I'm really thinking here is that S is GI over FI for all I. Right? This means numerator over denominator. Right? So the S has denominator all the FIs. Right? The condition I'm making on S here is that the S here multiplies elements in ID into omega x, and I'm identifying with OX. So this means that the FI here are the denominators of S, and whereas the GI are the numerators of S. Right? And so, you know, there's this sheaf OX divided by ID, and that's just D. Right? If I set the place where ID is 0 is just the subscheme D. Right? And there's also the place where OX divided by this numerator is 0. Right? And I can call this N. So this D and N are completely different. I mean, this S is really a linear equivalence from the divisor D into the divisor N. So, you know, in some picture it might be, you know, this is, if this is the point D, and this is the curve X, then it could be that, for example, that S looks like that and that D looks like that. Right? And but this S is a linear equivalence. It's a linear system. It's defining a linear system, D twiddle Z. Right? So OX, OD, and ON are not at all isomorphic. Right? These are just completely different subschemes. However, the trick is that ID is isomorphic to IN. Right? IN is by definition the image of ID, and you know, with a little twist, you can assume that S is injective, and so we have this isomorphism. Right? And the Gorenstein condition, I'm not saying which form of it I'm using, which definition I'm using, but you can track down the condition that D is Gorenstein from this. So here I've got X. If I put, sorry, here I've got Y. If I put S equals 0 in Y, is isomorphic to the scheme N in X. Right? That's just, so I go into Y and I put S equals 0. So that's the same as not adjoining anything at all and setting all of these GIs equals 0. Right? And so, you know, this is a pseudo proof. It's not a complete proof. It's just a sketch. The idea here is that because D is Gorenstein, it has a this ID has a resolution of some special shape, and therefore IN is just isomorphic as OX module. Right? And because D has the good property, then also N has the good property. So this proof is not completely correct, but it's not all that difficult to make it correct. So I'm not going to say anything more about the proof. So I mean, the thing I want to emphasize is this is a very, very general statement in commutative algebra. So it was done by Kustin and Miller around 1980-ish in a paper called I think it's something like constructing big Gorenstein ideals from smaller ones. And it was done again by my student Papadakis and Reid around 2001-ish. So this is in, you can find this paper in lots of different places. You know, follow the link from my web page. Okay, so let me say how you use the theorem has almost nothing to do with how to prove it. Has not much to do with how you prove it. So in some ways you can sort of forget that I said all that. You know, forget the theorem and the discussion of the proof of the theorem, and just let's see about how we apply it. So in almost all the applications today, and in the applications in 2 weeks' time, in the applications. We take x to be graded, so not local. And then we take d and d in x are graded, and again not local, right? And then there's going to be an extra condition that I want. Kx is Ox of some number Kx, and Kd is Od of some Kd, right? And it's completely essential to be able to do this in the graded context with Kx greater than Kd. Okay, so when I stated the theorem, I said local ring. X and D were spec of local ring. So now they're spec of not of a local ring, but of a graded ring. I mean graded means graded in positive degrees. Right? So this is the category of rings that I have spoken about here before, graded rings in positive degrees. Right? So one of these sheaves, saying that X is Gorenstein is saying that the ring has a dualizing module. So, you know, this is omega X, and this is omega D. Right, and these are modules over the graded ring OX. Right, and the assumption I'm making, I'm assuming they're Gorenstein, which means a lot of X's vanish, and these guys are locally free. They're locally free sheaves with a single generator, and the generator has a naturally occurring multiplicity. I'll give examples. In examples, there's nothing scary about this at all. Right? But I insist on this. Okay, so example. And so, you know, what this is really about is projective geometry. It's the idea of projection in projective geometry. So let's start with S3 in P3, non-singular cubic. Right, and I want to take L in S3 a line. Right, so S3 has Ks is -1, and L has KL is -2. Right, so this number here, Kx, is greater than, this is -1, -1 is greater than -2. Right, And so the thing I assert is I can contract L to a point. So of course you know that you know this by Castelnuovo's contractibility criterion. So L is isomorphic to P1 and L squared is -1. But I'm going to contract it inside this category of graded rings. Right? So let's say that L is given by x equals y equals 0. And so then S is a surface containing a complete intersection subscheme xy, and so therefore S is in the ideal xy. So I can write S, for example, as ax plus by. I want to write ay minus bx. Every time I do this, I will put them in a different order. It doesn't really matter. Right? So A and B are quadratic. Yeah? And so now I write down S is A over x is equal to B over y. So this S here is the same as that S over there. It's the same as the S that's... So, what is S? Well, the S here, in terms of the A here is naturally graded of degree 2, and the X is naturally graded of degree 1. And so the S is naturally some graded object of degree 1. On the other hand, he has a pole. He has a pole along Y. So I can think of the S as being in OS of 1 with poles on L. Right? The global section of course, I mean. Yes? Yeah, what I'm saying is completely elementary here. He's naturally graded of degree 1, and when he's written like this, he naturally has a pole along L. So the S, I can think, if I want to, I can think of this as being something which takes the ideal of L into OS of 1, or I can think of this as something that's taking IL minus 1 into OS. I'm sorry, I'm not quite sure why I wrote that. I really want this S to go from IL into omega S of omega S twisted by right. And so anyway, so in terms of the graded rings, this is something which is taking the ideal x, y, maps into this the omega of S, and then because these guys here have degree 1, so I want this to go down to omega of L, which is OS of minus 2. Right, so I want this to go down to a basis in there. So I have to tensor this by O of 2, and this means I have to tensor this by O of 2 as well. Anyway, don't worry too much about this. What I'm doing is very clear geometrically. Right, so because this surface S contains the line L, his equation can be written like this. Because the equation like this expression A divided by x and B over y equal as rational sections of OS of 1. Right, so it makes sense to take a new P4, this is P3 adjoined the element S. And the new surface T inside there given by Sx equals A and Sy equals B. Right? So this surface S here is an intersection, Q1 intersect Q2, 2 complete intersection. Right, and the point P, this point, the point P sub S, so this is the point 0, 0, 0, 0, 1. So this is P4 with coordinates, the same as the old coordinates, x, y, z, t, and a new coordinate S. Right, so PS is this new point 0, 0, 1. So this T is necessarily non-singular there, right? We don't know too much about how A and B behave, but if I'm standing at the point PS, then I can solve these equations. So the differential of these two equations with respect to x and with respect to y at this point are non-zero. So the Jacobian determinant is non-singular. So this in T is a non-singular point. Yes? And so what's happened is that so what's another way of saying what's happening is that I've got this point PS in T, which is 2 complete intersection in P4, right? And then I'm doing a projection here to P3, and then inside here I'm getting S, right? So the fact that the equation can be written like this in terms of these, the x and the y are the guys that's a 0 at the tangent space at the point PS. Right, so this is x. This is this thing which is called ay minus bx equals 0, and this is the guy called sx equals a, sy equals b. Yeah. So if I was doing affine space, if I'm doing the affine cone over S and the affine cone over T here, then there's a coordinate ring here, K homogeneous of S, right? And the coordinate ring here is this guy here, adjoined S, divided by 2 equations, right? So it's a particular case of this construction. Right. So I'm telling you I have this, you know, basically subtle, fairly subtle and complicated result in commutative algebra, and I can apply it to this completely trivial problem in geometry. But the point is that in this example, in this, whatever it's called, ay minus bx example, there's absolutely no, it works just as well. It works even if S is as singular as it likes, as singular as it can be. Right. The thing I'm using here is that x, y is a regular sequence, and that ay minus bx is a regular sequence, and nothing else. Right? So this works if you have a very badly singular surface or whatever you like. Right? And also it works at the S that doesn't have to be a cubic surface. I'm going to do later when S is a quartic, K3 surface, and then I'm contracting, and the difference is that this element S, then S, will be homogeneous, but not homogeneous of degree 1 anymore. Okay. Okay, so this is just a very simple example. Let me say there are many applications now. So So let me do just a couple of parallel projections. So suppose I want to really think in the same kind of naive terms here. So suppose V is in Pn, and suppose that he contains xy equals 0. So in other words, this V is I'm thinking of this V as being a hypersurface of some degree d, right? And he contains this xy equals 0, so he's like this. But let's suppose he contains x1, y1, but also x2, y2. Right. So I can. What I want to do is say that there is a projective space Pn adjoined and Pn plus 2 with adjoined coordinates x, s1 and s2, where s1, x1 equals sum a1 and s2, s1, y1 equals b1, and the same with 2. Right? And so I just say do exactly the same constructions that I did here. Then because V contains the hypersurface x1, y1, I can write V is A times y1 minus B times x1. And then I can get S1 equals just the obvious thing here. And then similarly S2 equals. Right? We haven't finished. This is not construction. This is only part of a construction. So I need to assume also that V is contained, the equation of V. So let's V is F equals 0. I want to assume that F is in the ideal x1, y1 times x2, y2. So this is the parallel assumption, right? I don't know if you can understand what's happening here. I'm assuming that V contains this codimension 2 complete intersection x1, y1. I'm assuming also that he contains x2, y2. So by the rules, he contains the intersection of these two ideals. He's contained in the intersection of these two ideals. He's contained in this guy and he's contained in this guy, so he's contained in the intersection. So the thing I want, in addition, is that he's contained in the product. Yes? And so this means that F is A x1, x2 plus B x1, y2 plus C x2, sorry, you know what I mean, y1, x2 plus D, y1, y2, right? and the expressions here, and you can write out, this is an exercise, the equations for S1, S2. So I told you how to do them. I said take this equation V and write them as something times x1 plus something times y1, right? And then write out corresponding equations for S1. Now do the same with S2. And so I have to divide this up into stuff divisible by x2 and stuff divisible by y2 and write out those equations. But there's another equation there and a fifth equation, S1, S2 equals something. So, well, you know, for example, if I have a cubic surface and I have two different lines in it, right? So this is an example, S3. Then I'm going to go up here to T5 in P5, del pezzo of degree 5, and he needs 5 equations. Right, so I told you how to get 2 equations for S1, 2 equations for S2, and then 1 equation for product S1, S2. And you can find this by from Pfaffian. Right. So on the one hand, this equation exists. These variables S1, S2, and the equations they satisfy exist because I have a theorem. Because at the back of this, there's this Christian-Miller projection theorem. Right. On the other hand, this is a perfectly pleasant little calculation. Write out the 4 equations that you can think of, and then figure out what the equation S1, S2 must be. Right? This has got to be a Pfaffian. Then take all 5 equations and assemble them into a single 5 by 5 Pfaffian matrix. I'm not going to do the exercise. Right. So this is again applying the theorem to do something which we already know is true. Right, so everybody already knows the del pezzo surface of degree 5. They know the sections of Grassmannian 2,5 intersect a number of hyperplanes. Right, but there's one of the applications of this is by Neves and Papadakis. And so they say the following thing, which is in some ways is quite curious. It's quite a crazy construction. Something you have to be a kind of algebraist to want to do this. But what they say is, let's take V4, degree 4 hypersurface, inside P7, and the P7 is x1, x2, x1, y1, x2, y2, x3, y3, x4, y4. Yeah? And so I have 8 coordinates in P7, and I write them out as x1, x1, I'm thinking of them as in pairs, and I want the V to contain the 4 codimension 2 linear subspaces x, I, y, I. Right, so call this pi, this is P5. So is the ideal, is the variety of xi equals yi equals 0. And I want this V, I'm going to say I want this V here not just to be contained in the intersection of these 4 ideals, but in the product of the 4 ideals. So let's take V4 to be a general element. This is just a general linear combination of 16 monomials in product xi, yi. Right? So in other words, I take monomials like x1, x2, x3, x4, and x1, x2, x3, y4, etc. 16 monomials, and I take just a general linear combination. Okay, then by applying the theorem, right, so here I've got V4 in P7, right, and it contains these pi i's, right, I can take this up into P. Now I'm adding 4 variables, so this is going up into P11, and it's weighted with the same variables as before, and then 4 new variables of degree 2. Right, and here there's some W, and this is inside there. Sorry. So the coordinate ring of the homogeneous coordinate ring of W, K homogeneous of W, is generated by K of this x1, y1, x4, y4, and then these new elements S1, S2, S3, S4. Right, divided by an ideal, and the ideal has generators given by Si times Ai, sorry, so I've got x1 S1 equals A1, y1 S1 equals B1. This is exactly as before. Right, and then I have the same for all values of I. Right, so this is how many equations it is. This is 8 equations, and another however many it is, S choose 6 equations, Si, Sj. Right, and these equations can all be obtained as Pfaffians from these, in exactly the same way as I described over there, can be described as Pfaffians. Right? So let's not worry too much about the algebra. Let's say, what is this geometrically? So geometrically, this is the V4 here is a hypersurface in. It's a six-fold hypersurface, and it contains 4 of these P5 planes. Of course, it's got to be just a little bit singular. It'll be a little bit singular, for example, where 2 of these planes meet. But let's not worry too much about that. There is a theorem here saying that this ring can be constructed. Yes, and what it really does is it takes these planes, it takes the planes pi I, it blows them up to make them into Cartier divisors on V, and then if you blow up a plane on a variety, it changes the variety a bit, but it doesn't change the plane. After that, these are exceptional of the first kind, and so these just contract. So the pi I gets, there's a rational map here, this is birational map. It's not a morphism because it blows up points here, and then these points get to the pi in there, and the pi are 0, 0, 0, 0, and then 0, 1, 0, 0. This is the Si. Right, and they are 1/2 of 1, 1, 1, 1, 1, 1 orbifold points. right? And the W is non-singular, right? Quasi-smooth. Right? So, you know, this is just, you know, we have an algebraic gadget, namely this unprojection theorem, and so if I want to, take lots of these planes contained in the hypersurface and contract them to points, right? And it so happens there, because this one is degree 4, so remember this is KV is O of minus 4, and also K of W is O of minus 4. So this is the Varenstein projection property, right? They're in slightly different spaces, and this one's got orbifold singularities, but nevertheless, right? So that's exactly what this Varenstein unprojection is doing. Yes, and so what Papadakis and Neves want so now they say if I take this W, intersect H1, intersect H2, intersect H3, intersect Q, where Q does not pass through any of the PI, this is a non-singular surface, and it has PG equals 5, and K squared equals 12. Right, so this is, you know, I mean, here's the construction. This W guy here is projectively Varenstein. So he's, you know, the W exists independent of these constructions and these calculations. The W exists by the theorem. Right, I have a theorem, so I'm allowed to contract these maps here. And locally in the neighborhood of each of these planes, I'm just getting these points. Right, so I've got this variety in projective space. I can just start cutting it. Right, so I'm cutting by 3 of the hyperplanes. So I've reduced this number from 8. 8 minus 3 is 5. Right, and the canonical class here has gone up from minus 4 plus 1 plus 1 plus 1 plus 2 to plus 1. So K is O of 1. Right, and the K squared is 2 is also easy. So each of these planes increases the degree of the variety by, so this is degree 4, this had degree 4 plus 4 times a half. Right, and each of these points increases the degree by a half. You know? And so they go on to find Z mod 6 free action on this, so I'm calling this T, so that T divided by the Z mod 6 is Campidelli. So this is one example, but we now have many other examples. There's so Neves and Pignatelli have another. So you know, this is sort of, you're doing this projection many different times, and separately, Sahel, my student Sahel, who was here, Iqbal, have similar constructions. Right. So so look, I want to emphasize one point here, which is there was a theorem, you remember, and the theorem had this X and D in its data, right? And the subtle point is not the theorem, is how to set up the data. Right. So our WCU project is called Constructing Algebraic Varieties, and as everybody knows, if you want to construct a hypersurface, then just go ahead, write down an equation. In general, if you want to write down something in higher codimension, you have some work to do. And so this, the theorem replaces one construction with the construction of y. So the problem of the constructing y with the problem of constructing x and d, and there's nothing easy about this. So the if the construction of y is obstructed, if the moduli space of y is exceptional dimensional, bad in some way, then the x and the d will likewise be bad. So it's not, the theorem is not really doing anything. The theorem is just translating one problem into another slightly different problem. And it so happens there are lots of applications of this x and d. So so not especially parallel unprojection, but we have this paper called Tom and Jerry, which I'm sure you'll be hearing about more when Gavin Brown is here. So here we construct approximately 300 formulas of Fano threefolds of codimension 4. So I'm not saying the fact there are 300 of them is particularly impressive, but we're really using this unprojection technique as a method of constructing variety, and also as a method of analyzing possible constructions of varieties. So in this case, we get results that are sort of more or less definitive about the existence of these formulas of codimension 4 Fanos. So let me say one or two more things. So I have this paper. If you go to my website, plus threefolds, plus I think it's something like graded rings of birational geometry. So this is a big paper, 2000, I think, 2001, I'm not quite sure, which already contains a lot of these ideas and a lot of, sort of tutorial material. So some of the stuff I said here was quite rough. I rushed through it quite quickly. Read this if you want to see some more details. And so, there are lots and lots of these problems, including classical problems in how to construct algebraic surfaces, should be best studied by this, technique of unprojection. So let me finally give. I said this word parallel. So the point about the parallel projections here. So over there, for example, I start off with my variety V, and before I start, the V already has these planes pi I, and the planes pi I exist inside V and are independent of each other. So in this case, the 8 of them here form the 8 equations of these two planes. The two planes, each of these linear subspaces needs 2 equations. If I take these 2 equations plus these 2 plus these 2 plus these 2, these form coordinates in P7. So in particular, they form a regular sequence. And so in this case, the equation of V is automatically contained in the product of the ideals, not just in the intersection, right? But so parallel here means that before I start doing these multiple projections, the centres already exist. So there's something else called serial projection, which we'll be doing a lot of, serial unprojection. So when you do electrical networks, you have parallel networks and you have serial networks where you do things in series. So here the idea is that the first unprojection provides the divisor for the second unprojection. So let me just give a baby example of this, so that you can see that this is not the same thing as parallel unprojection. You can think of it in some ways as being having infinitely near centres. So first of all, let me start off again exactly as I did before with a hypersurface in P3, which is of the form XA. Look, I'm sorry, I never get this right. YA minus XB. Right, so now A and B are cubics. Right, and S4 contains the line L, which is x equals y equals 0. Yes, so this is a nice, possibly non-singular surface in P3 containing a line. Right, and so there's an unprojection here. There's a map here which goes from T in P4, for P4 is 1, 1, 1, 1, 2. This is the new guy, S. Right, and this T is just given inside here by Sx equals A and Sy equals B. Nothing could be simpler. Right, so this is just exactly the same construction as I did, just weighted in with slightly different weights. Okay, now suppose that S has a node on S, on L. Right, so instead of being non-singular, suppose that here's my line L, and as it goes along, the surface S has 0. So this means that A and B have a common 0. Yes. So then, when I do this T, this T now contains a new line. So it's actually a line P1, 2 through the orbifold points. Right. So look, we know that this is a K3 surface. This line L here, if it were non-singular, the line L would be a -2 curve. Yes, -2 curve. It's natural to want to contract it. I contract it to a point, and then it's just an ordinary orbifold point. It's a quasi-smooth point of this T. Right. However, suppose that there's a line. Suppose that there's a node here. So suppose that there was an A1 singularity already on the S. Right. Then before I contract the L, I have to blow up the L. And so what I'm doing here is I'm blowing it up first. I'm getting a -2 curve here and a new -2 curve. Then I contract this down. I get, so here is the, in this case, T has this shape, and there's this line L through it. Right? And now I can, now unproject this new exceptional curve. So the exceptional curve for the first blow-up, this new L prime. L2. Right, and when you do that, you're going to get the new surface will be in 1, 1, 1, 1, 2, 3, because this canonical class, the canonical class of this is minus 3. Right? So the only thing I'm doing here is I'm explaining this word serial. Right? So here, you can imagine that I start off with a surface in P3, I unproject it here and make a surface having a node. Right? However, if there were a little singularity somewhere along the line L, then this T contains a new curve. It wasn't a curve on S. It's been blown up out of S. So in other words, the first unprojection I did here provides the center for the second unprojection. Right? And, you know, if this were not an A1 but an AR singularity, I could continue doing this several steps. Okay, so the second lecture is almost has very little to do with the first lecture, the independent